Lesson 30, Particle Physics. Part 1, Antimatter. For every kind of particle in the universe, there is a corresponding kind of antimatter particle. Antimatter particles have the same mass as their corresponding matter particle, but opposite charge. For example, the electron and the positron have the same mass, but the electron has negative the elementary charge, and the positron has positive the elementary charge. Let's look at some common particles and their antiparticles. The proton, P+, has positive 1 elementary charge. The antiproton is a negative version of the proton with the symbol P-. The neutron is neutrally charged, and the antineutron is also neutrally charged. The antineutron has the same mass as the neutron, and the only way to tell them apart is they annihilate each other if they come into contact. In addition, the neutron is made of quarks, and the antineutron is made of antiquarks. The electron symbol is E-, and its charge is negative 1 elementary charge. The positron has the same mass as the electron, but it's positively charged, 1 times the elementary charge positive. The neutrino has a symbol, looks like a V, but it's curly on both sides, and the antineutrino is the same, but with a bar on top to show that it's the antiparticle. The only real way to tell the neutrino and the antineutrino apart is that they annihilate each other if they come into contact. When a matter particle and its corresponding antimatter particle collide, they annihilate each other. This means the particles cease to exist. The total mass of the particles is converted into energy. But when a matter particle comes into contact with an antimatter particle of another type, they do not annihilate. You could take a proton, P+, and have it meet a positron, E+, and nothing would happen. You can combine matter particles with matter particles to make elements. So for example, an electron orbiting a proton is hydrogen. An antiproton being orbited by a positron is antihydrogen. You could construct the entire periodic table using antiprotons, antineutrons, and positrons, and make an antiperiodic table. Example: calculate the energy released in the annihilation of a positron-electron pair. The mass of the electron is 9.11 times 10 to the negative 31 kilograms. An electron and positron both have the same mass, so the total mass of an electron and positron combined is 2 times the mass of the electron, 2 times 9.11 times 10 to the minus 31, which is 1.822 times 10 to the negative 30 kilograms. We can determine how much energy is released when this total mass is converted into energy as the particles annihilate. E equals mc squared. So we take this mass, 1.822 times 10 to the negative 30 kilograms, and multiply it by c, which is 3 times 10 to the 8, squared. This gives an energy equal to 1.64 times 10 to the negative 13 joules. We can convert this into electron volts by dividing by 1.6 times 10 to the negative 19 joules per electron volt. This gives an energy in electron volts equal to 1025000 electron volts. This is an energy equal to 1.025 mega electron volts. So, when a positron and electron annihilate each other, 1.025 mega electron volts of energy is released. Pair production. When a gamma ray with enough energy hits a nucleus, it can turn into a matter-antimatter pair. This is how matter can be created. This picture of pair production was taken in a bubble chamber. A bubble chamber is a tool used to observe the movement of particles. It consists of a vessel filled with superheated transparent fluid, most often liquid hydrogen, and can be used to take pictures of the paths of electrically charged particles moving through it. It's important to note that these are electrically charged particles. Neutral particles and photons cannot be seen traveling through a bubble chamber. They have invisible paths. If a magnetic field is applied in the bubble chamber, scientists can use the curved paths of the particle to determine their charge and mass. For example, in the picture to the right, a magnetic field is directed into the page. Determine which particle is the electron and which particle is the positron. Neutral particles, such as neutrons and photons, cannot be seen in a bubble chamber, so we can assume initially a gamma-ray photon was coming in, and at this moment it collides with something and produces a positron and electron pair. The magnetic field is into the page. If we take our left hand and we point our fingers into the page and our thumb down in the direction of the particle's velocity, our palm has to point to the left. This tells us the particle on the left, this one, must be negatively charged, which means it's the electron. If we use our right hand and point our fingers into the page, our thumb down in the direction of the particle's velocity, our palm points to the right. This tells us the particle on the right must be the positron because it has to be positively charged. Part 2. The 4 fundamental forces. Physicists believe that 4 fundamental forces govern all interactions in the universe. The first is the gravitational force. You've already learned about this when you studied universal gravitation and gravitational fields. The gravitational force acts between objects with mass. It governs the movement of the planets and moons in our solar system, as the planets are attracted to the sun and the moons are attracted to the planets. It has an infinite range, which is why it's the one we see the most often, because it can extend over large distances in space. It is the weakest of the forces. Really, the only reason why we do see it so much is because of its infinite range, and the fact that it's only attractive. Next is the weak force. It acts between fundamental particles, quarks and leptons. We'll learn about those in a bit. It is the shortest range of all 4 forces. It can only reach a distance about 10 to the negative 17 meters, which is really just about halfway across a neutron. It's the second weakest force. It's actually stronger than gravity, but because of its short range, we don't see it very much at our size. Next is the electromagnetic force. You've already studied this when you studied electric fields, magnetic fields, and electromagnetic radiation. It acts between charged particles. It has an infinite range. We don't see it as often as gravity because it has attraction and repulsion, and the attractions can cancel out the repulsions, leading to no net force. It's the second strongest force. It is significantly stronger than gravity and the weak force. Finally, we have the strong force, or sometimes the strong nuclear force. It is the attraction of quarks to each other. It's what holds the quarks together. The quarks make up the nucleons, the protons and neutrons, to form the nucleus. It has a very short range, about 10 to the minus 15 meters. It can really just reach about halfway across a uranium nucleus. But it's the strongest of the forces. It has to be strong because it has to balance out the electromagnetic repulsion between the protons, or the nucleus would fly apart. Force-mediating particles. In quantum physics, energy is carried by particles. For example, the photon is a particle of light energy. It travels with wave-particle duality in packets of energy. We call these packets photons. Modern physics extends this idea to say that the energy of each of the 4 forces is carried by its own unique particle. The force-mediating particles are, for the gravitational force, the graviton. For the weak force, there are 3 particles, the W+, W-, and Z0 particles. The electromagnetic force is carried by the photon, which you've already learned about quite a bit. And the strong force is carried by a particle called the gluon, because it glues the nucleus together. Part 3, the standard model of matter. After the discovery of subatomic particles, scientists started to discover a whole bunch of different particles, muons, tauons, photons, neutrons. All of these particles amounted to what scientists called the particle zoo. They needed to have some way of organizing the particles into a system that made sense. This system is called the standard model of matter. According to the standard model of matter, there are 2 kinds of particles, fermions and bosons. Fermions are particles that can't be in the same place at the same time. This is a law called the Pauli exclusion principle. Fermions obey the Pauli exclusion principle. Bosons are particles that can be in the same place at the same time. They don't obey the Pauli exclusion principle. We'll start by looking at some bosons. All the force-mediating particles are bosons. The gravitron, the W+, W-, Z0 particle for the weak force, the photon for the electromagnetic force, and the gluon for the strong force are all examples of bosons. These are particles that don't obey the Pauli exclusion principle and therefore can be in the same place at the same time. The Higgs boson represents a famous recent discovery in particle physics. It's the boson that gives particles mass. Interactions with the Higgs boson is what determines whether a particle is going to be massive or massless. Next, we're going to look at some fermions. Quarks and leptons are the 2 categories of fermions. We'll start with leptons. Leptons are fundamental particles that are not made of anything smaller. The electron is the most famous of the leptons. Other leptons include the electron neutrino, which goes along with the electron, the muon and the muon neutrino, the tau and the tau neutrino. All the top row of this table have a charge of -1 times the elementary charge. The bottom row, the neutrino row, all have no charge and minimal mass. Because every particle has a corresponding antiparticle, there are 6 corresponding anti-leptons. The positron and the anti-electron neutrino, the anti-muon and the anti-muon neutrino, and the anti-tau and the anti-tau neutrino. Because antiparticles have the same mass but opposite charge of their corresponding matter particles, the top row of this table has a charge of +1 elementary charge, and the bottom row still has no charge and minimal mass. Quarks are the building block particles. They can combine to make larger particles. There are 6 known quarks: the up quark, the down quark, top quark and bottom quark, charm quark, and strange quark. Up and down make most ordinary matter that you encounter on a day-to-day basis. The top row of this table have a charge of +2/3 the elementary charge. The bottom row has a charge of -1/3 the elementary charge. Because every particle has a corresponding antiparticle, there are also 6 antiquarks: anti-up, anti-down, anti-top, anti-bottom, anti-charm, and anti-strange. The top row has a charge of -2/3 the elementary charge, opposite to their corresponding quarks, and the bottom row has a charge of +1/3 the elementary charge. The 6 quarks and the 6 leptons represent the 12 fundamental particles of matter. These are the particles that all matter you encounter are made up of, and they can't be broken down into smaller particles. Quarks are building block particles, which means they can be made into other particles. Particles that are made up of quarks are called hadrons, the particles built from quarks. There are 2 kinds of hadrons, mesons and baryons. Mesons are made of 2 quarks, 1 quark and 1 antiquark combination. Baryons are made of 3 quarks. 2 famous baryons are the proton, which is an up quark, and a down quark, and the neutron, which is made of a down quark, and an up quark. This fermion chart is found on your datasheet for Physics 30. It shows the charges of the up quark, the down quark, the anti-up, and the anti-down quark. Example: the pion is a meson made of an up quark and an anti-down antiquark. What is the charge of the pion? The up quark has a charge equal to plus 2/3 the elementary charge. The anti-down quark has a charge equal to plus 1/3 the elementary charge. The charge of the pion is equal to the charge of the up plus the charge of the anti-down. This is 2/3 the elementary charge plus 1/3 the elementary charge, which is plus 1 the elementary charge. This means the charge of the pion, made of the up and anti-down quark, is plus 1 elementary charge. Next we have the proton. The proton is a baryon made of 2 up quarks and a down quark. What is the charge of the proton? The proton is made of up, up, down. The charge of the up quark is 2/3 the elementary charge. The down quark has a charge of negative 1/3 the elementary charge. If you add these charges together, you get the charge of the proton. 2/3 plus 2/3 minus 1/3 is equal to 1. Plus 1 the elementary charge. This is the charge of the proton. Finally, we look at the neutron. The neutron is a baryon made from 2 down quarks and an up quark. What is the charge of the neutron? So the neutron is down, down, up. The down quark has a charge of negative 1/3 the elementary charge. The up quark has a charge of plus 2/3 the elementary charge. If you add these charges together, you get the charge of the neutron. Negative 1/3 plus negative 1/3 plus 2/3 is equal to 0. So the charge of the neutron is 0. Part 4. The Standard Model and Radioactive Decay. Radioactive decay processes happen as the result of failure of the forces that hold the nucleus together, the strong force and the weak force. Let's look at the strong force first. Protons are repelled from other protons due to the electromagnetic force. The role of the strong force is to hold the nucleus together against the repulsive electromagnetic force. The strong force is an attraction of quarks to other quarks, and the attraction of nucleons to other nucleons. The strong force is much stronger than the electromagnetic force. However, it has much shorter range and can't reach across larger nuclei. When the strong force fails, the nucleus breaks into pieces. Alpha decay is an example of failure of the strong force. In alpha decay, the nucleus ejects an alpha particle, 2 protons and 2 neutrons, and becomes a smaller nucleus. Fission is another example of failure of the strong force. In fission, the nucleus breaks apart because it can't hold itself together anymore. The weak force. The role of the weak force is to help quarks maintain identity. It keeps top quarks, and down quarks. When the weak force fails, a quark can change identity. Up turns to down. So in a proton, which is an up quark, and a down quark, an up quark would turn into a down quark, turning the proton into a neutron. Or down could turn to up. In a neutron, we have a down quark, and an up quark. When the weak force fails, a down quark could turn into an up quark, turning the neutron into a proton. Beta decay is a failure of the weak force. In beta positive decay, a proton turns into a neutron and releases a positron and a neutrino. So we have a proton made of an up quark, and a down quark. turning into a neutron, which is up, down, down. In the process of turning into a neutron, the quark that changes from up to down releases a W plus particle. This is the boson that transmits the weak force. The W plus particle has a very short lifespan. It decays quickly into a positron and a neutrino. Here's the equation we can use to describe beta positive decay. Up, up, down turns into up, down, down plus a W plus particle. W plus decays into a positron and a neutrino. The full process is written as up, up, down yields up, down, down plus a positron plus a neutrino. In beta negative decay, a neutron turns into a proton and releases an electron and an antineutrino. So we start with a neutron, and the neutron turns into a proton as one of its down quarks turns into an up quark. The quark that changes releases a W minus particle, the force transmitting boson for the weak force. The W minus particle has a short lifespan. It decays quickly into an electron and an antineutrino. Here's the equation used to describe beta negative decay. Up, down, down decays into up, up, down plus a W minus particle. The W minus decays into an electron and an anti-electron neutrino. The full process looks like this. Up, down, down decays into up, up, down plus an electron and an anti-electron neutrino.